Hello everybody, hopefully you can hear me, and on the second feed hopefully you can see some questions. So I thought I'd sort of give you a little bit of a lead into and get your revision started. So I thought I'd go through some questions today. I'll do them on the I'll go through on the board, so you'll have to be quite keen on the camera. I will zoom in to the board as much as I can. I would usually do this on my whiteboard in my room, you know, my electronic one, but I forgot the cable today. So yeah, that's the end of that idea really. Right, okay, so we can go up to about here. Yeah, that'll do there. Right. So if you look at the screen capture of this feed, we'll go for question one to start with, nice and easy. Calculate to two decimal places the present value of £4,000 due in 8 3/4 years, assuming the following effective interest rates. 0.5% per annum for time between 0 and 5, 0.25% per month between 5 and 6.5, and 2% per half year for time after 6.5. Right, okay, so if you want, stop the video and have a go, and I will get stuck in to it. Right, bring that down to there. Okay, so I'll freeze. Right, let's draw a timeline. If you can hear some vibration, that's the air conditioning. I can't do anything with that. I've tried, but I don't know what happens if it was freezing cold in there, but maybe there's some overall control somewhere. Right, give this a go, this microphone. Okay, so we've got a payment out here of £4,000. That's at 8.75 years. Then we're told that between 6.5 and 8.75, we've got an interest rate of 2% per half year. Effective. And then between 5 and 6.5, we're told we've got an interest rate of 0.25% per month effective. And then between 0 and 5, we've got 0.5% per annum. Okay. Okay, right, good. So we know we're going to discount this thing back, so we're going to come back all the way to here for that. So we're just going to work out the various discount factors. Okay, yep, that's good. I'm just making sure that's clear enough for everybody. So to find the present value, we need to find V. This V, if we call this period 1, period 2, and period 3 here. So period 1, discount between 5 and 0. We work in years for that, so it's per annum. The second one is between 5 and 6.5, which is 1.5 years, which is 18 months. We've got a monthly rate there, so we'll do that to the power 18. And then finally we multiply them to V3, which is for 2.25 years, and we've got a half yearly rate of 2%. So 2.25 years is 4.5 lots of half years. Think about that. All right. Okay, let's just do the calculation. And of course then, sorry, we've got to times that by 4,000. So 4,000 multiplied by 1.005 to the minus 5 multiplied by 1.0025 to the minus 18 multiplied by 1.02 to the minus 4.5. So I'll let you do that calculation. I haven't got my calculator with me. 3412, something like that. 3412. Okay? Easy start for us. So hopefully that got you in the mood. If it didn't, let's hope this one will. Right, so question 2. So back to the screen or the other feed. A company expects to receive 10 level annual payments of 22,500 from a customer starting on 1st of July 2019 and finishing on 1st July 2028. The current date is 1st January 2018. Assuming that I12 equals 6% per annum, calculate the present value of this set of payments. Okay, right. So first thing, let's draw a timeline. So we're here, so what date were we? Here, 1st of January 2018. So 1/1/18, 1/1/19. Next one, now small, zoom in, hopefully you'll be alright, you've got better eyes than me. And then the first payment is on 1st of July 2019. Okay, so it's 1/7/19. And then the final payment was on the 1st of January 28. 1st of the 7, 28. 22,500 there. And everywhere along to there. So, have a think, how many payments have we got? Do it on your fingers. Or we do 28 minus 19 plus 1. 10. So, we've got 10 annual payments. Okay, right. So, what are we going to be careful of here? First of all, so we know we need to do an annuity. So, we'll work out the annuity to here. Or, we could work it out to year before, but we won't bother with that because we've got a little bit of complexity to do. So, we're going to find, so first of all, we'll find the annuity there. So, that's an A. Is it a double dot or not? Double dot. It's annual. 10 payments. And here in front of it is 22,500. 22,500 multiplied by A. So this gives us the present value of each of the 22,500s on the 1st of July 2019. Now, let's have a look at the interest rate. Think about that. So, we've given a nominal interest rate. What was it again? 6% per annum. That's handy. So, it's 6% per annum. And in full, if you remember, that's payable monthly. All right? So, what are we going to do with that then? You'll need some keen eyes to read that bit. Anyway, so these nominal rates, to make them useful for discount and accumulating, which is what we're doing here, we're discounting here, we need to turn this into an effective rate. So if you can remember my terminology I use, I say we're going to turn that into I to the 1/12 down there. That's an effective rate. If you remember, you divide the 6% by the frequency, which is 12. So therefore, the effective rate is 0.5% per month effective. Which is great. Thanks very much for that. Question? Okay. So, we're working in annual units here. So we need an annual interest rate I. How do we get from the half-yearly one to the yearly one? 1 plus I to the 1/12 to the power of 12 minus 1 will give us I. And I is going to equal, I don't know, 6.2 or something like that, isn't it? Probably a bit more than that, actually. Nope. 6.1, so 6.16778% per annum effective. So I'm going to go back to red now. I'm going to use that. So let's go and do our annuity. So 2250 multiplied by 1 minus 1.06. Hopefully this is working. (16778) to the minus 10 over 0.0616778 over 1.0616778. Right. So something else then here. So we had I. Remember D equals I over 1 plus I. And if we remember for the annuity, AX, A double dot X equals 1 minus V to the X over D. So that's why I've gone and done this 0.0616788 over 1.0616788. Okay, good. So that gives us our annuity, and that is giving us the present value here. So we know, I'm going to do this bit in blue. Well, no, actually, I'll do it in black here. So we've got another 18 months to go back. We've got a monthly effective interest rate here. So we know this is 1.005 to the minus 18. So then I'll put that extra discount on here, multiplied by 1.005 to the minus 18. And the answer comes out I haven't actually got the answer. It's just wrong on this solution here, which is a bit unfortunate. So the answer is going to be something like 150,000. All right. So I'll just put C 150k. I haven't got my calculator with me, and I'm not doing it on Excel, so I've set the computer up there. Okay, right. So you might want to fast forward. So I need to give the board a clean. Right, so let's have a look what's next then. Question 3. Alex and Anna each need £10 per week to live on. They decide to ask their dad for their weekly allowance. I think I do know these girls. Alex agrees that she will receive £10 per week for 1 year. Yeah, she certainly would. Anna noted from FT.com, she started young, that she could receive 3% per annum effective interest if she put the money into a savings account and then took out the £10 from the account each week. She therefore asked for £500 at the start of the year instead. The first £10 paid to Alex, but paid out by Anna, is at the end of the first week. Okay. So they both need £10 at the end of each week. One is going to receive it as she goes along, and the other one is going to have a lump sum up front and then gradually run that down. So, A, does Anna end the year in surplus, or does she run out of money? Okay. So, I'll let you have a think about that for a few seconds. You can pause the video, and then I'll get on to going through the solution. Okay, right. So we'll get started on this. I'll take my solution with me, I think, on this one, just so it's got a few more numbers on than before. So let's have a think about what Anna does. Because the question is about Anna. It says, is the £500 enough? So there's a couple of ways we could do this. We could do it numerically by starting at 500 and crunching through 52 weeks. So effectively accumulating by a week's interest. To start with 500 multiplied by a week, 1 plus a week's interest, minus the 10, and then multiplying that by the next week's interest to go all the way through 52, see if it's greater than less than 0. Or we can use some of our mathematics which we've used. So we're going to go and find the present value of Anna's outgo. Okay, so it's 10 per week. So present value of Anna's outgo. Anna doesn't like outgo. She'd rather just not see this and Dad to pay it, but that's another story. So 10 annuity, 52 in arrear. That's it. We've been given I equals 3% per annum. So let's go and find I monthly, I weekly. So we'll just call it IW, which is equal to 1.03 to the power of 1 over 52. We'll assume just 52 weeks. I know years a little bit longer, 52.18 I think, in a normal year, minus 1. And that gave us, what was it on here? 0.05686% per week, effective. Okay, so we go back up here, 10 multiplied by 1 minus 1.0005. Yeah, that's right. 686 to the power of minus 52. And then that's over 0.000585686. Comes out at 512.24. So what does it imply? Present value of the outgo is higher than the present value of the income, the 500, which is given to Anna at outset. So she runs out of money. I don't think she'd go to prison. I think there'd be another source of money at the end of that. Right, okay. If she does have a surplus, how much would it be at the end of the year? Well, she hasn't got a surplus. She's got a deficit. So that's the answer. However, if we work this out, what is the deficit at the end of the year? Once again, it's all straightforward when we've got our financial maths. So the net present value is minus 12.24 at time 0. So to go and find the deficit at the end of the year, we simply just take our net present value and accumulate it to the end of the year. Minus 12.24 multiplied by 1.03. Whatever that answer is. Let's have a look. 12.61 minus 12.61 is her deficit at the end of the year. Okay, right. One more question. Right, I'll clean the board. You have a quick read of that. Question 5. Get started on it if you can. Right. Company expects to receive the following 3 payments from a customer. 10,000 on the 1st of April 2017, 4,500 on the 1st of July 2018, and 3,200 on 1st of January 2022. So quite a range of dates. The current date is 1st of July 2016, so 1st of the 7th, 16. This date represents time 0, and hence 1st of July 2017 is t equals 1. So t is in years. Assume that the discount function vt runs from 0 to t and is given by v to the t equals 1 minus 1/60th t squared. Okay. Good. Right. So hopefully we've seen these. Find the value of each payment as at the 1st of January 2020. So think about what this is all about. So this is discount functions. And accumulations, or accumulation factors, I should say. Accumulation factors. Good. Okay, so let's get started with this. I haven't looked at the solution yet, I should do, but the solution's not how I would write it out. So let's do a timeline, first of all. I think that's the best one. And we'll just do one cash flow to start with. Let's take that first one. So it was 10,000. So it's 10k on the 1st of April 17. No laughing matter in that one. Oh, brilliant. Right, so we were told that time equals 0 is 1st of July 16, didn't we? Yep. So that's time 0. So how far has this gone forward? Well, this is, so 8, 9, 10, 11, 12, 1, 2, 3, 4. So it's 9 months, so this is time 0.75. Let's have a little sneaky look on here, make sure I'm not going too mad. No, I'm not. Okay, we need to find the present value of that, or, well, in this case, that'll be the accumulated value on the 1st of January 2020. So we're looking for x, call x. Good. So what time's that then? So it isn't 4 years. It's 3.5, it's 3.5, isn't it? Yeah, so that's time 3.5. So we've got to be a little bit careful. A lot of people will just use that v and they'll say, oh, I'll use the vt from here, between this here and here. How long we've got a discount? So that's 2.75 years. So that's a 2. So I'll do V 2.75, which is wrong. That is not how these things work. Vt is equal from V from times 0 to times T. Okay? So we're starting here, so we need V 0.75 and we need V 3.5, and then we need to combine them to find what the discount is in between. And I'll show you how we do it for the first one, and well, maybe all of them, to be honest, depends how much time I've got. So we start with the accumulation factors. A 0 to 3.5 is equal to A 0 to 0.75 multiplied by A 0.75 to 3.5. We rearrange that so we get the ones with the zeros on one side. So we'll now have A 0.75, yes, 3.5, and that equals, that's there, so the A 0 to 3.5 over A to 0 to 0.75. And then we need to use V A and B equals 1 over the accumulation factor A and B. Alright? So for this first one, this means that 1 over V 0.75 to 3.5, which is what we want here, is equal to 1 over V 0 3.5 divided by 1 over V 0 0.75, and we can see that, if you remember that we've got these here, our VTs, so that goes to the top, so V 0.75 over V 3.5. So to find our present value, to find our accumulated value, we need, that's going to be 1 over that, of course, so it's 10,000 multiplied by 1 over V 0.75, 3.5, which is equal to 10,000 V, over that, so it's V, where are we? Sorry, I've gone mad here. So it's over that. Yeah, so V equals the 3.5. Sorry, everybody, I'm just going absolutely mad at the moment. That comes to the top. Yes, that comes to the top there. So I should have written this out. Sorry, everybody. So that becomes V 0.75, 3.5 equals V 3.5 over V 0.75. So the 1 over that, of course, now the 0.75 comes over the top again with a V 0.35. Now I know I've done quite a lot of working on that, and I could have got there quicker, but I want to explain it fully. Finally, we need to actually do the V's. So V 0.75 equals 1 minus 1/60th times by 0.75 squared, and then V 3.5 equals 1 minus 1/60th times by 3.5 squared. And the answer comes out something like 12,448, 478. 12,478. If you're doing it on your calculator. Okay, well the principles are pretty much the same for the other two cash flows, so I'm not going to do that. How much time have I got? I haven't been thrown out yet, so I'll keep going. So the answers for the other two, just in case you do it, for the 4,500, the value is 5277.52, and then for the 3,200, that was 1993.67. Okay. Right, B, remember now we've got a net present value at the 1st of January 2020, so we need to accumulate that for 3.5 years to whatever the time is, whatever T is on 1st of July 2023. Okay, now just going to go on to C. This is a slightly different question. So let row T represent a continuous payment of £200 per unit time. This is paid between T equals 1 and T equals 4. Now let delta S be the force of interest and is represented by delta S equals 0.1 plus beta S. Write down an integral that represents the accumulated value. I don't think you have to solve this, you just have to write this down, I think. Yeah, just write this down. Write down an integral that represents the accumulated value at time t equals b, where b is greater than 4. Okay, for this continuous payment. So have a go at that. Freeze the video. Make me more frozen than normal. Right. Okay. So let's go. So let's write down the stuff we know with these integrals. So the first thing we do is write down the payment integral, and that's between 1 and 4. And we're given that rho t is a constant, is 200 per unit time. We've got 300 of them. Next thing, the discounting or the accumulation integral. So I put the integral there. Now what are we going to do? We said we're going to accumulate this to time greater than 4. So okay, that's fine. So first of all, we know we're going to accumulate this, so let's put delta S ds in to start with, and then we'll just finish the integral by putting dt on, where dt is every time between, infinitesimally small time between time 1 and 4. Right, okay, so where are we going to go to with these? So we're accumulating. So for each time t, between 1 and 4, we'll start there, and then we'll accumulate for a set amount of time. How long are we going to do that for? Well, we're going to accumulate to time b. So let's test this. Remember, I always do this through test and practice, the Maxwell method, as I call it. The physicist, by the way, from the 1800s, that Maxwell, all right? Not any other one. So let's think about it. So let's let t equals 1. So we're going to start the thing off. We start right there. We've got a rate of that per annum. So therefore t goes into there, and we're going to accumulate from time 1 to b, where b, we know b is greater than 4. Okay, that's fine. What about when it is 4? When t is 4, so there accumulates a little bit less, time 4. Good. So I think we've got something which is making sense now. So we can now just drop in. I think we had an expression for delta s. So we score 4 marks. Delta s was something easy, wasn't it? 0.1 plus beta s. I'll put that in there. 0.1 plus beta s. And we're done. Now, of course, we can go and solve that if you want. A little bit problematic, not disastrous, but we won't do it. We won't do it here because, of course, the reason I say that is because we've got this beta s here, which we're going to integrate. So that becomes beta over 2 s squared. But of course, that's an exponential. So we know that integrating higher power exponentials can be a little bit problematic, not massively, but usually we just do them numerically. We haven't worked on numerical methods in this course. I know you do it elsewhere anyway. So it would be a little bit more of a problem, but it doesn't matter because we haven't got to do it here. So anyway, right, a few questions done. I hope that's a decent start for you, and yeah, hopefully I'll do some more videos, and feedback if you find them interesting. If you don't, yeah, that's fine, I won't bother doing any more, so feedback that as well. So thanks very much.